Hi, this is Ming-Yao from Ozone Engineering, and in this video I'll be demonstrating how to set up a 2D explosive simulation in Ansys Autodyn. Let's get started. So we're going to grab a 3D step file into our Ansys Workbench environment. The 2D analysis in the Autodyn for multi-material Euler analysis is not available in the standard explicit dynamics. But we can use it to set up our model and then finish the simulation with Autodyn by connecting the model up like this. Let's go ahead and edit the geometry in SpaceClaim. Here's our model. Let's look into it. We have a casing, some explosives, and a spherical inert material. 2D analysis in Ansys needs to lie on the XY plane. So we're going to create a few planes to slice up our model. Let's get rid of this part, and then we'll split this model again. Hit escape key, select this model, cut it here, and let's get rid of this part. Okay, what I'm doing here is creating a cross section on the XY plane. We can then copy these surfaces here. We still have the 3D model. I'm going to suppress this for the physics, and we'll rename this for easier identification. So this surface is my case. This surface is my explosive, and we'll call this one a inert material. Okay, now we can go back to the Workbench project page and let's start defining some materials. This is the Ansys Engineering Data Material Setup tool. We want to go to the Autodyn or Explicit Dynamics materials because this is where all of our explosive models are stored. Okay, so here are the explosive, these are all the Autodyn materials. You can see we have various types of aluminum. And if we're looking for explosives here, we can, for example, find our C4 explosive material. Click on this plus sign, copy some material to the engineering, to the current simulation. There's also compound B, compound A. And that's a concrete model, and you can see we have different types of LX with all the explosive properties. So I'm only going to copy these over. Let's take a look at the copper we have here. There's two. There's a linear shock material for copper. We wanted to find a failure model for these, so I'm going to go to my nonlinear materials. There's just a few examples of it, and we can copy the nonlinear copper alloy over, and maybe in our general materials, we can, for the inert material, maybe we'll make it a polyethylene. So I've collected a few different materials from different libraries. So you see we have all of the C4 data, copper nonlinear with a plasticity curve, and polyethylene as a linear material. We want to have both the copper and the polyethylene to fail at a certain strain rate. So the copper one is, we can define the failure model using one of these models available. I'm going to just specify a plastic strain of 2, which means that once the copper reaches a plastic strain of 2, it will fail. For polyethylene, we can specify. I'm going to have to create a bilinear isotropic hardening curve here, and if I don't have the data, typically I look at our Granta selector tool. This has a huge, they call it a material universe. So all kinds of materials available in the Granta selector. All kinds of material properties are available in Granta selector. So if I type in, let's see, polyethylene ethylene. So there's a lot of different types of polyethylene material. We have some polyethylene for molding and extrusion, and we want to know what the maximum tensile strength is. Yield strength. So the elastic limit is about 1e to the 7. So let's put in 1e to the 7 is the strength. Yep. And we can specify a modulus of maybe something similar, a couple of orders of magnitude below that. So we have some a plasticity curve like this. Once we have plasticity defined, we can specify the same type of plastic failure model. Okay, so that's setting up our simulation. We need to make sure Ansys recognizes that this model is a 2D model rather than a 3D shell model. But now we're ready to go ahead and set up our explosive simulation in Ansys Explicit. Okay, this is the model as is imported into Ansys Explicit. We're only going to use this tool to set up the simulation. So here is going to be, this will be a copper piece. We'll have our C4 piece here, and then this is the inert material, which will be my polyethylene. We want to remove all the contacts because we're not going to be using any of these actual models. These are the Lagrangian parts. We're going to be running this as a multi-material 2D Euler model. We want to specify a time limit, so 5e to the minus 5 should be good. It's a very small explosive that we're going to detonate here, and the rest I typically leave on default. Ansys will adjust it as needed. The output, typically I want a few more points, but we can adjust that later. You can see I still have a question mark here because Ansys thinks this is a, oh, the other thing we need to change is the 2D behavior under geometry. We want to make sure this is set to axisymmetric so that they know this is a symmetry of axis. The axis of symmetry is the y plane. We still have a question mark because Ansys wants some sort of a boundary condition. So I'm just going to put in a pressure of 1 megapascal. We're going to rewrite this later, but this gives us enough information to move this from Ansys Workbench Mechanical to Autodyn. So right click here, update, and this will write out an Autodyn input file that I can then open in Autodyn. Okay, Autodyn's axis symmetry is the x-axis, but you can see Ansys, when we link it together, it automatically flips the model. So now we have the x-axis as the axis of symmetry. Going down this list here, we have all of the materials set up. You can see the materials are set up correctly. We can plot contours of pressure, for example. We can show boundaries and detonation points. So everything is set up here. The first thing we want to do is define a new part. Right now, these are Lagrangian parts. We're going to create a new one. I'll call this the explosion part. This will be a 2D multi-material Euler domain, and we want to specify the x origin and the size. For that, we can go back to geometry and look at the bounding box properties. Let's see. So we know this is about 20 millimeters by 7 millimeters, and if we click on one of the corners, it shows us where this is located. So this corner is at 0, minus 14, 0. So we want the starting point on the x-axis to be below that. So I'm going to start at minus 20. And y will be 0. So we know that this part is about 20 millimeters. We start about 5 over here, so maybe I'll make the total Eulerian domain to be 30 millimeters here. By this is 5 millimeters, 6 millimeters over here. So maybe we'll do 30 by say 16. And now we can go back to our Autodyn interface. So it's going to create a box here, and let's do 300 by 160 as the number of divisions. So there will be 60,000 nodes and 48,000 nodes and 48,000 elements. And we'll fill everything here with the material void. Okay, so this is our Eulerian domain, and we can adjust this, delete it, change the size, etc. That should be just fine. Right now the explosion is all void. We want to fill this with the material from our Lagrangian parts. So we're going to do a part fill. We're going to take all the parts, and we'll use the material in the parts to replace the material in the void definition. So that's it. Let's go ahead and delete the parts that we don't want now. And you can see the material is the same. You can see there's a little bit of stair stepping around the circle because the multi-material Euler is a Cartesian mesh in the XY axis. So you have some stair stepping, but it does a good job of capturing the shape of the model. So next we want to specify the boundaries. Right now there's one boundary, so we're going to modify this. We'll call this I'll call it outflow. And we're going to set all the materials to be equal. So this is an Euler boundary condition, and we want to specify it on all the different sides. So let's go back to the parts, and we want to click on boundary and assign the I boundary to be outflow. Let's make sure it's plotting boundaries. So that is the boundary. Let's do the second I one. This will be at 301. That should be on this side, so that's going to be an outflow boundary as well. And on the J side, we want the maximum, so 161. Right, so you can see we have the boundary specified on all three sides of it. This is a axis symmetry, so we don't need a boundary there. And we have the boundaries now, so all we need is a detonator somewhere over here. So let's go back to mechanical, and we can identify where this point is. So this point is at minus 13 millimeters. And let's click on detonation. We'll use an indirect point detonation. And this will be, let's say, minus 12. We'll put it maybe a millimeter away from the end here. Okay. So that's the detonator. So this will detonate, causing the explosive to detonate, and then that's going to crush our plastic as well as modify change the shape of the casing. So this is all set up now. The controls are all gathered from our previous simulation, the setup prior to this. This is in milliseconds, and we want to set the output. One of the nice things about Autodyn is that it lets you see what's happening during the simulation. So I'm going to refresh the display every 10 cycles, and we want maybe 50 results. So this is it. Let's go ahead and save the project. And let's go ahead and click run to see what's happening with this simulation. Okay, so I forgot to specify the interaction here. There was an error. We need to have no interaction in this model. You can see it's changing a little bit. I'm going to stop the analysis, and we're going to plot the pressure. Okay. Now let's run this again. So you can see a 2D analysis runs really fast. It shows how the pressure wave, as it travels through the material, the explosive, and goes into our soft inert material, wraps around, bounces back. So we can stop this here, and we can look at a few things. There are many additional materials results available. So alpha shows you where the detonation happened. You know, what part have been detonated. If we go to this low step 102, you can see this is the detonation front. A few cycles later, it's traveled there, and a few cycles later, it looks like that. So we saw pressure. We can look at temperature as well, and many different types of post-processing available here. So this shows you a quick video on how we can set up a 2D really fast explosive simulation. This type of technique is often done for looking at detonators and shaped charges, explosively formed projectiles and things like that. And you can use this tool to look at what happens in the kind of near field, near where the explosion happens. And Autodyn has some very specialized capability to remap the results from one analysis, even a 1D to a 2D to a 3D simulation. So there's a lot of advanced techniques. And I'll try to put those into videos in the future. In the meantime, thank you so much for watching this video. If you like this video, please subscribe to our channel. And if you have any questions, please contact us at ozeninengineering.com or ozeninc.com. Have a good day, and take care. Bye-bye.